NASA's asteroid mission, officially known as the OSIRIS-REx mission, has just completed an analysis of the asteroid Bennu. The spacecraft was launched in 2016 and arrived at Bennu in 2018. The mission's primary objectives included a study of the composition and mineralogy of Bennu, understanding its geologic history, and gathering samples of the asteroid's surface material. Additionally, the mission's objective was to learn more about the origins of the solar system and the potential impact hazards of near-Earth asteroids. Bennu is a carbon-rich asteroid that is believed to be a remnant from the early solar system, making it a time capsule of the solar system's formation. By analyzing the composition and mineralogy of Bennu's surface material, scientists hope to uncover clues about the conditions and processes that existed when the solar system was formed. This includes understanding the role of volatile and organic compounds in the early solar system, which are essential for the development of life. Additionally, Bennu's small size and weak gravity mean that it has preserved fine-grained material and structures that have been undisturbed since its formation. By studying these preserved materials, scientists can gain a better understanding of the processes that led to the formation of asteroids and other celestial bodies in the early solar system. Moreover, asteroids like Bennu are believed to have played a role in delivering water and organic molecules to Earth, which are essential for the development of life. Scientists can also investigate the potential role of such asteroids in seeding the young Earth with the building blocks of life. The OSIRIS probe contains several onboard cameras and scientific equipment to map the distinct topology of Bennu. OSIRIS-REx camera suite, OCAMs, consists of 3 cameras, a MapCam, a Polycam, and a SamCam, that capture high-resolution images of Bennu's surface. These images are used to create detailed maps of the asteroid and identify potential sample collection sites. OSIRIS-REx laser altimeter, OLA. OLA uses light detection and ranging, LiDAR technology to create 3D maps of Bennu's surface, providing precise topographic information that helps the spacecraft navigate and target sample collection locations. OSIRIS-REx visible and infrared spectrometer, OVIRS. OVIRS analyzes the sunlight reflected by Bennu to identify and map the asteroid's mineral and organic material distribution. This helps scientists understand Bennu's composition and its relationship to the early solar system. OSIRIS-REx Thermal Emission Spectrometer, OTS. OTES measures the infrared energy emitted by Bennu to identify minerals on the asteroid's surface and study its temperature variations. This data offers insights into the asteroid's composition and geologic properties. Regolith X-ray Imaging Spectrometer, REXIS. REXIS uses X-ray detection to map the elemental abundances on Bennu's surface. Touch-and-Go Sample Acquisition Mechanism, TAGSAM. The Touch-and-Go Sample Acquisition Mechanism, TAGSAM, is a robotic arm on the OSIRIS-REx spacecraft designed to collect samples from the surface of the asteroid Bennu. The sample collection process involves several key steps. It uses a nitrogen gas system to disturb the regolith, surface material, and capture the resulting material for return to Earth. Before attempting to collect a sample, the mission team used the spacecraft's cameras and other instruments to survey Bennu's surface and identify potential sample collection sites. These sites were carefully chosen based on factors such as the regolith, loose surface material, properties, slope, and accessibility. When the spacecraft descended toward the selected site, the TAGSAM arm was extended toward the surface, and the sampling head made contact with the regolith. The sampling head is a circular device with a collection chamber that uses compressed nitrogen gas to disturb and collect surface material. Once the sampling head makes contact with the surface, a burst of nitrogen gas is released, which agitates the regolith, causing some of it to be captured inside the sampling head. The spacecraft's instruments and cameras were used to confirm that a sufficient quantity of regolith had been captured. Once the sample is successfully captured, the TAGSAM arm is stowed, securing the sample in a containment vessel for the return journey to Earth. The entire process happens in a matter of seconds, and the spacecraft autonomously carries out the sample collection without direct human intervention. This approach minimized the risk and uncertainty associated with the challenging task of collecting asteroid material from a remote and dynamically evolving surface. With the samples safely stored, the OSIRIS-REx spacecraft made its journey back to Earth, arriving in September 2023. The collected sample materials were retrieved and analyzed in laboratories to help scientists understand insights into the early solar system and the formation of planetary bodies. Capturing samples from diverse types of terrain on Bennu was crucial for several important reasons. Bennu is an ancient asteroid that has preserved material from the early solar system, providing a window into the conditions and processes that prevailed billions of years ago. By collecting samples from different types of terrain, scientists can obtain a more comprehensive understanding of Bennu's composition, structure, and geological history. The diverse samples will help researchers understand the asteroid's surface evolution, the distribution of varied materials, and the potential impact of external forces such as micrometeoroid bombardment and space weathering. Bennu's surface is characterized by varying degrees of roughness, including boulders, ridges, and other irregular features. These uneven terrains pose challenges for the spacecraft's ability to make safe and precise contact with the asteroid's surface during sample collection. Variations in terrain topography can affect the stability and safety of the spacecraft during sample collection. The presence of steep slopes and uneven terrain features poses challenges for identifying safe and accessible sample collection sites. Sloping surfaces can affect the stability of the spacecraft and the precision of sample acquisition, necessitating careful consideration of surface topography to minimize the risk of slippage or loss of contact during the sample collection process. Addressing these surface hazards involves thorough reconnaissance, detailed mapping of the asteroid's surface, and the careful selection of sample collection sites. Prior to sample collection, the spacecraft conducted a comprehensive terrain assessment using its onboard instruments, including its cameras and LiDAR systems. This assessment provided detailed maps of the asteroid's surface, enabling the identification of potential sample sites with stable and level terrain. The mission team analyzes the topography and slope characteristics to select sites conducive to safe and secure sample collection. The mission team employed stringent criteria for site selection, prioritizing areas with minimal slope inclination and surface roughness. Sites with excessive slopes that pose a significant risk of spacecraft slippage or instability are excluded from consideration for sample collection. The spacecraft was equipped with autonomous navigation and guidance capabilities, allowing it to make real-time adjustments during descent and contact with the surface. During the descent and contact phases, the spacecraft's thrusters are precisely controlled to manage its velocity, altitude, and attitude relative to the asteroid's surface. This ensures that the spacecraft maintains stable and controlled contact, minimizing the risk of unintended sliding or loss of traction. Thruster control played a critical role in managing the spacecraft's position and stability during sample collection maneuvers. Redundant systems and safety margins were incorporated into the spacecraft's design to enhance stability and mitigate risks. What OSIRIS-REx found. After a 7-year mission in space, the OSIRIS-REx spacecraft returned its samples to Earth on September 24, 2023. Samples collected from Bennu, consisting of rocks and dust collected from the asteroid's surface in 2020, will offer scientists a view into the past, when the Sun and planets within our solar system were forming about 4.5 billion years ago. The samples were found to contain both water and carbon, key ingredients that helped life begin on Earth. Studying Bennu provided a unique opportunity to unlock the mysteries of the early solar system, shedding light on the processes that shaped our cosmic neighborhood and set the stage for the emergence of life on Earth. Thank you for joining Time Pilgrimage on this adventure. And as always, don't forget to like, comment, and subscribe to our channel for more captivating time and space-related content.